And so what are you having open your slides?
Yeah, can you open us?
Where is your slide?
I don't know.
You don't know? Which one is
This one.
this one?
Yes.
This one.
Okay, so hi everyone, my name is Kai Han Tang, and today we present fully dynamic active-based signature for circuit from code. And this is a joint work with Professor Linh San, Dr. Nguyễn Hoàng, Professor Phan Dương Hiệu, and Professor Hoa Song Wang and Dr. Yan Hong Su. So a brief information about this talk. We get rejected 9 times among previous conference, including Eurocrypt, Crypto, Isocrypt, and TCC and PKC previous years. And this is the 10th time, and we get accepted here in PKC Sydney. So this is the outline of my talk. First, I will record a preliminary about active-based signatures and Stern protocols. And then I will discuss about our contribution, including full active-based signatures and the technique for revisiting Stern. And finally, we provide our result regarding this paper. So for the preliminary about active-based signatures, so an active-based signature allows a signer to sign based on an attribute, and at its signing, the user need to show that his attributes satisfy a public predicate B, then he can produce the signatures. So in such a signature, we require the following properties, including correctness. Privacy is mean that among all users satisfying having attributes satisfying predicate B, the user is anonymous. And enforceability, it means that the user who does not know the predicate satisfy sort of B cannot create the signatures. So during the history of ABS, we have the following development in 3 different directions. The first one is for expanding the expressiveness signatures. Expanding the expressiveness of signing policy, and this include different class of policy like non-monotone set structure, bodic depth circuit, and unbound arithmetic spectrum. And regarding the functionalities, there are more results improving on making traceability and leakability or revocability. And regarding the computational assumption, we have other results for bearing-based and post-quantum active-based signatures. So another preliminary about Stern protocol. So Stern protocol is a zero knowledge argument knowledge from Stern, and this one address the problem to prove the linear relationship between three components: a matrix M, a vector V, and a witness W. So in this protocol, the prover would like to prove that he possesses vector W such that M times W is equal to V, and this witness W has an additional constraint that the weight of W is equal to W, some small W. So in Stern technique, they require 2 components. The first one is a random mass R in order to mask the witness so that they can prove the linear relationship between MW equal to V. So in this way, they set a vector Z equal to the mass vector of W, which means W plus R, and then show that MZ is equal to V plus MR. So in this way, the prover can show that MW is equal to V, and to show that the weight of W is fixed by some small W, the prover use a random permutation to permute the witness W and show that the permuted witness is also have the fixed weight small W. So so in fact, we observe that the following 2 things. The first one is that for the random mass to mass W, is it necessary to be uniformly in the set of on vectors? And second, for the for the random permutation to hide W and to show the weight, is it necessary to be in a group of symmetric in a symmetric group? So this is our contribution for the paper. So the first one, we propose a new definition of attribute signatures. This is called fully dynamic attribute signatures, and by fully dynamic, it means we support joining users, updating keys, and revoking key. And we also provide a construction of course by fully dynamic attribute signatures. And this construction is post-quantum and support arbitrary circuit. And it's also secure in quantum random variable model. And the second contribution is for revisiting Stern protocol for caused by cryptography. And we provide a new framework for capturing previous work of turns. And we also achieve a good efficiency for the mask and the permutation used in the protocol. So regarding full dynamicity of attribute signatures, our challenge in this talk, in this paper, is to unload the revocation of user, and then to do this one, we require something like time related update of the system information in the system. So regarding the syntax of fully dynamic attribute signatures, we decide following the previous work from fully dynamic group signatures, and in this syntax we have a register to record on joining and using the system, and also whenever we update the system by joining new members or revoking previous member, we update the system information, and then we also associate every signature by an abort tau. This means the current abort, so that whenever the signer return a new signatures, he needs to associate with certain abort, and the verification also requires this abort to verify. So the privacy is similar to previous attribute signature that require the anonymity of the user among all attributes satisfy a predicate. However, in our design, we also make it secure against malicious generated keys. And regarding enforceability, so an adversary cannot create new signatures with path keys. It means that the key not go through the key generation process. And so in designing the cost by fully dynamic attribute signatures, we require the following components. The first one is a Merkle tree accumulator. This one is to show that the user is among the members in the system, and a commitment scheme to commit private information of the user, including the keys and the other information related to the keys, and a standardized zero knowledge argument of knowledge for the signature. It means we construct this signature by using this zero knowledge group to and transform it in the Fire-Samir paradigm to make signatures. So in our design, we assume that the attribute of each user is S, and we commit to the attribute by we commit to each attribute to get the public key D, and then for each signing, we need to show that the public key D is among on user having valid public keys, and then when signing, we need to show that D is among the members, and D is a valid commitment, and also we need to show that the predicate on input attribute S satisfies. And then to make it secure in the quantum random oracle model, we show it by using unroot transform from previous work. Okay, so now because we use the sunlight zero knowledge argument of knowledge for this signature, so in our next contribution, we revisit Stern to make a more efficient construction of Stern protocol. So like as I said previously, we need to use a mask R to mask W, and also we need to use a random permutation to hide W, and for pose question, uniformly sampling R from on binary string is not necessary, and also uniformly sampling permutation from symmetric group also not necessary. So an observation is that we can, if we have a witness W of odd weight, then we can use a random mass of odd weight, and then we observe that when masking W with this R, then the resulting string is uniform on binary string of even weight. So to generalize then, we first capture the witness W in some valid set, and then regarding the random mass and the permutation, for the random mass, we capture the random mass in some set R, and then we show that the mask vector W, W plus R is uniform in Z, in some order set Z, and for the permutation, we use a finite set S to capture it, and to capture a relationship between the for the weight, we propose other three different functions, f prime and f2 prime here, and then to show instance, we try to show the following. First, in order to show that W is among the set, the valid set, we need to show that the function f with respect to input, the value phi, the component phi, and the witness string W is also in valid set. And second is that whenever component phi is sampled from some finite set S, then the function f with respect to phi and W is uniform in the set valid. And for homomorphism, this means we also need to show that the homomorphism satisfies. So here f prime with respect to R and f2 prime with respect to R when taking the sum is equal to f with respect to R plus Z. So so we apply this generalization to proving the knot and gauge. So for on pooling circuits, using the N gauge, the knot N gauge is sufficient to universally realize on pooling circuits. So here we apply the N gauge as follow. So the knot N gauge for S1 knot and S2 is equal to S1 plus times S2 plus 1. So our purpose is to prove that a secret S3 is equal to S1 knot and S2. So we define the encoding function with respect to the three values S1, S2, S3 as in the slide. And then here we also define the valid set as required from our generalization that to contain on and encoding S1, S2, and S3. So we observe that S3 is equal to S1 not S2 if and only if W here is the encoding of S1, S2, and S3, and this encoding must belong to valid. And the second thing is that the last entry of W is equal to 1. So if we can achieve this observation, then we can show that S3 equal to S1 not and S2. And here we apply for here we make the mass and function for proving as follows. So the finite set S here is not a permutation anymore, but it's a set of over 3 elements in Z2, and the set R, and R is the set of on odd weight vector over 4 elements, and Z is the set on even weight vectors over 4 elements. So to define f prime and f2 prime for some protocol, we first define the function T to permute the 4 element vectors according to E1 and E2 by the following slide in the slide. So and then we define f prime, f2 prime based on that function T by masking them with E3. So after defining this set and R and Z, the sets R and Z, we can achieve the standard protocol with smaller cost compared to previous result in Eastern zero argument models. So here is our final result. So in this result, we applied our resistance to build fully dynamic attribute by signature. So here we achieve the smallest signature size, and we are also secure in a quantum random oracle model. And our assumption used here is the cost-like assumption, and also fully dynamic. Thank you.
Another question: how with the fully support the development and the retention?
You can enroll new case, update the case, and revoke the case. So it means fully dynamic.
Oh, I mean,
You can enroll new members, update, for example, update the key of the members, and you revoke the member from the system. This means the member no longer can sign.
Mention the time, the echo.
Yes.
What is the echo?
The avoid mean that because when you revoke the members, right? So the members with the previous key cannot sign anymore. So you need to update the system information, and to update the system information, you need to update the time too.
So you mean the next level, the user need another. This must be to match the echo.
Actually, if you revoke the user, right, then the user no longer can sign. So
but if it is not revoked, it has used.
yeah, he's revoked it, but he still keep the key. He still keep the old key.
Oh, but his key is not matched with the echo.
Yes, not matched with the.
But if it is not revoked, it can still sign.
Yes, if not revoked, it then can still sign.
But like one, so like as far as from your presentation, you're considering you were considering Boolean circuits with 9 gates.
Yes.
And can you like also generalize to, for example, arithmetic circuits, or you have to work with Booleans necessarily?
Actually, our Songro is more familiar with cost-based. So for arithmetic circuit, now I don't know whether I can generalize on arithmetic circuit.
Okay, so if there are no more questions, let's thank the speaker again.
Thank you.
So the second paper being presented today is register attribute-based signatures. And Ian Zhang is going to give the presentation. Please go ahead.
Hello everyone, my name is Jian Zhang. The topic of my presentation is registered attribute-based signature. It's completed from the collaboration of several authors, Jun Zhao, Qi Zhu, Jin Qinggong, and Jie Chen. They come from East China Normal University and Shanghai Qizhi Institute. So let's start from a well-known primitive attribute-based signature. I'll call it ABS for short. In this system, there are two parties, signer and verifier. This signer has a secret key SKY associated with his attribute. This attribute could be the identity address or any other. So he can use this secret key to generate signature with respect to some message M and policy X and send it to verifier. The verifier will proceed with the verification procedure, and he will accept this message M only when PXY equals 1. I mean, attribute matches the policy. This procedure is completed using master public key MPK. So let's pay attention to the generation of SKY and MPK. Both of them from authority. This authority is powerful. It runs a setup algorithm to generate MPK and MSK. This MSK can be used to delegate all secret keys corresponding to any attribute. So our motivation just exactly falls on this authority. If some adversary can break the guard of authority and steal MSK, it can delegate any secret keys and forge any valid signature to convince this verifier of any message and policy. So in this work, we propose the notion of registered ABS. It is inspired by the work of Hoppenberger et al. At Euro Capital 2023. Previously, Okamoto and Takashima has proposed the notion of decentralized ABS, but it also suffers from fiasco problem when the amount of sub-authorities exceeds some threshold. So in this work, we present the definition of registered ABS and gives concrete construction from standard linear assumption. Then let's see the definition. In this system, the authority is replaced by a curator. This curator also runs setup algorithm, but it just generates a common random string, CRS, and give it to signer. With this CRS, the signer will generate a pair of public key and secret key locally. And it just sends this public key and his attribute to curator. And for curator, it will proceed the registration procedure. It updates MPK for the verifier and help key HK for this signer. This HK is just for assisting the signature generation. All this registration procedure is fully transparent, and this curator will store no secret. So in register ABS, there is no MSK, and all secret keys are generated locally by signer. There is no worry about fiasco problem. The rest procedures about signing and verifying is just similar to ABS. Then we define the security of registered ABS. It's called unforgeability. Here, the adversary has access to three kinds of oracle. The first oracle is just for registering secret keys given attributes provided by adversary. Challenger will generate public key and secret key and update current MPK. The second is for corrupting secret keys. It means any system user may collude with the adversary. The last one is signature generation. It means the adversary has access to any previously issued signature in this system. So finally, this model requires the adversary to submit a forged signature with respect to some message M star and policy X star. And it requires this signature should be valid, and all attributes Y corresponding to corrupted secret keys does not match this policy, and M stacks that have never been queried to signature oracle. So if all these conditions are satisfied, we say this adversary breaks the forgeability successfully. Then question is how to construct registered ABS. We propose the building block slotted register ABS. It's similar to registered ABS, but just require all signers in the system to register their public key and secret and attributes to the aggregator at once. And after collecting this, the curator will just update MPK and HK at once. After that, there is no users joining the system. So slotted registered ABS is just a static version of registered ABS. And with this tool, we can use it to construct registered ABS using power of two tricks, building multiple slotted registered ABS instances for different amounts of signers. Here L is the bound of number of of signers in registered ABS. Then we can make a reduction from the unforgeability of registered ABS to underlying scheme. So now all we need is just to construct a secure slotted registered ABS. Our technical line is inspired by the work of Kamado Takashima and at PKC 2013. And we try to transform the existing slotted register AB to ABS. Then we observe that in both parameters they share the same registration procedure. So these parameters can remain variable. The main difference lies on the signature generation and verification. In ABS, secret key and help key should be used to delegate signature, but in AB they are just directly to use for decryption. So for verification, we decide to treat the ciphertext in ABE as a verification text in ABS. It can generate from MPK and message and policy. Then we can use this verification test and signature to perform pre-decryption algorithm. So if attribute matches this policy, it can recover message correctly. So if this delegated signature can inherit the decryption ability of secret key and help key, this verification is feasible. Following this line, we have the following structure of help key and MPK. They are constructed from the predicate encoding. With this predicate encoding, it generates a pair of a tuple of matrices. The system will generate this matrix for each user and accumulate them into it. And the secret keys are hidden there. And the predicate coding has two properties. Alpha construction is used for our verification, and alpha previously is just used for security proof. Then we use this help key to and secret delegate signature by just embedding this secret key UI into an exponent of help key, and the verification text is just generated by simply new randomness into the each component of MPK. Then we verify the signature is generated from slot I. In step 1, we can cancel all cross terms from other slots, so that only parameters about under slot I are remained, and this step can be done via pairing. In step 2, we can use the alpha construction in predicate coding to check the tribute Y matches the policy X. And so that we can recover the secrets alpha I and UI in verification text. And in last step, we use them to cancel alpha UI in signature. If this signature is valid, it can recover alpha S correctly. So it seems that this construction is accomplished, but there is a problem. It's here in signature. We just embedding the UI into the signature, so it's complete liquid. And anyone can acquire it. So our solution is to add new randomness and new secret components to hidden this alpha I. Here CR and DI are new secret keys, and this hash value is generated from message and policy. Then we proceed the security proof. Recall that in the step 3, we will check alpha X is if our alpha X is recovered correctly. So if we can randomize this alpha in security proof, it will be impossible for the adversary to forge a valid safe signature. Then our analysis is as follows. First, we consider honest case. In this case, for each slot, honest slot I, the attribute y can match the challenge policy x star, and the adversary can allow the two query signatures to at each slot, except to each slot with respect to any message and policy, except for m star and x star. So with our solution, we can hide this UI, this XUI in signature, so that UI only appear once in this verification text, and it can hide the alpha in verification text, so that alpha in signature can be randomized in the view of adversary. So this is honest case. Then we can let's see the corrupt case. In this case, adversary has non-secret case UICID. So also this quality is not the and but attribute y does not match policy x star. Then we will use the alpha probability of critical encoding. It can hide the alpha I in verification text, so that alpha in signature can still be hidden in the view of adversary. Then the security we complete. At last, we present some open problems. It's focused on more passive predicates and higher security. And this is all my presentation. Thank you.
Allow the designer to create their own public-private key pair is great. But I'm wondering, should we sacrifice anything to achieve this great feature? Is there any particular limitation in registered ABS compared with conventional ABS?
The question is about the definition of registered ABS.
Is there any limitation, particular limitation?
Oh yes, yeah, yes, it has some efficiency limitations for registered ABS. Here, it's similar to registered AB. The master public key and the help key, their size should be compact. I mean, it should be polynomial logarithm L. At least L is the number of system users. And the update in registered ABS, it's updated numbers should also be logarithm in L.
So actually, I have a related question. So can you say something about the size of your CRS and the size of the signatures?
CRS. Oh, okay. CRS could be polynomial in L. Right. It is hard to achieve to compact CRS using pairing-based techniques, but it can be used to with lattice techniques.
And for the signature, do they depend on it?
Yeah, yes, we will explore it in the future.
Also, it is for communication. Have you considered the
Haven't this problem we have not considered.
That question? Well, let's spend this figure again. So that five minutes before it's at 17 and then 1 minute. But I think we're going very. Should we go a bit over time so that all right, so the third talk is on multi-signatures for ad hoc and privacy-preserving group signing by Anya Lehman and Kavit Rosbai, and Kavit is giving the presentation.
Thanks for the introduction. So let's start with the basic stuff. Signatures are used for authenticating a source of any data. And a common usage pattern there is you will have some kind of verifier, could be a server or any distributed system maybe. And our user needs to register after creating a key pair by using the public key of her. Here, Alice is the user. And whenever Alice wants to authenticate, Alice needs to sign the operation that she wants to authenticate for, and then send the signature to the verifier so that verifier can check the signature and verify. But in most of the cases, we need to rely on multiple parties to authenticate certain operation. Common use cases are in a public ledger, we need to create a joint account, or in any multi-factor authentication scenario, we need to rely on multiple devices, which means that we somehow need to rely on multiple secrets that are stored by different parties or different devices. Traditional method to solve this problem is threshold signatures. In a threshold signature scheme, again, Alice can create her own key pair and authenticate by using it. But whenever Alice wants to authenticate together with Bob, or form a signing group together with Bob, they can use an interactive key generation algorithm, which outputs a group public key and individual secret key shares for Alice and Bob. This can be repeated by Bob and Carol too, but the output here is a bit different for individual users because they have to keep a dedicated secret key share for each signing group or each signing context they create. So it means that they don't have long-term secret keys anymore. But this inefficiency in the key management creates an interesting privacy feature for them because a contribution of a signer in different groups are independent of each other, which means that contribution of a signer to different signing groups are mainly untraceable across different groups. So this gives some kind of privacy feature, even if it's a trivial privacy feature. And in the context of multi-factor authentication, or in a case of a public ledger use case, this is a nice property. Compared to threshold signatures, there's a recent approach to signing as a group, and this is called multi-signatures with key aggregation. Multi-signatures can only support the N out of N access structure, but it is still useful in many contexts. In practice, many joint accounts on public ledgers are kind of N out of N, and also in multi-factor authentication, we generally use two-factor authentication, so it's kind of 2 out of N, 2 out of 2 in most of the cases, so it works. And multi-signatures have a nice property as follows. In a multi-signature scheme, users just keep an individual key pair instead of generating new secret key shares for new groups. And whenever they want to form a group, they just run some key aggregation algorithm that takes the individual public keys as input and outputs a group. Here, Alice and Bob can just create an aggregated group public key as APKAB. And this can be repeated without needing to create a new secret key. The nice part here is that we still have the long-term secret key, then we can form groups, even if it's a restricted threshold setting. And the question is that, can we have the same untraceability feature as the threshold signatures? This is the question we want to answer, because if we could still have this untraceability, it would be helpful in the context of authentication for the end users, such as public ledgers or multi-factor authentication. In the literature, we couldn't find a formal analysis of these properties or formal definitions, but we found that there are certain informal claims about it. Actually, the first paper that proposes this key aggregation technique for multi-signatures claim that this could be useful for providing some privacy for the end users, as this key aggregation technique will hide the number of signers or individual public keys of the signers, so that they will be kind of they will have some extra privacy compared to other settings. But there's no formal analysis or definition of this property. So we want to define such privacy notion in the context of multi-signature, where we still keep some long-term key. And we defined it. After that, we saw that for the existing constructions, it's not achievable for some trivial reasons. And we defined a new type of multi-signature to achieve this long-term keys for unforgeability, but still have a similar untraceability across groups, just like threshold signatures. First, let me introduce the privacy definition we want to have in more detail. As I said, in the use case we consider, we want to create arbitrary groups together with other signers, and we want that the registered public keys in different contexts must be indistinguishable for each other, but obviously we'll also output some signatures for these public keys, so this should also be considered in the system. And we need to have some kind of indistinguishability game for it, and we will need some adversary to try distinguishing it. Since we are working in N out of N setting, we consider the adversary as an outsider to the challenge group, because if the adversary is inside the group, the adversary has to contribute to the signing sessions, which prevents having any privacy in the case of these sets, because the number of the signers will be revealed to any signer joining to the session. So the adversary has to be outsider in this case. But the adversary can be insider to any other groups in the system. So the adversary is only outsider in the challenge group here. And another key point is that the adversary needs to know the individual public keys in the system, because we want to make users able to join arbitrary groups, and individual public keys by nature as the same must be public in that case. And in such a case, we need to be able to create arbitrary groups as we defined before, and these aggregated group public keys and the corresponding signatures must be indistinguishable from each other. This is the property we want to achieve. For the existing works, we see that this is not possible to achieve because of mainly the key aggregation technique they use. They use a deterministic key aggregation technique, all of the existing ones. And there's a trivial attack against such key aggregation algorithm. Here I will just sketch it for Alice and Bob and their group. They will form their individual key pairs, and at some point they will share it with each other. They can just run the deterministic key aggregation algorithm to form a group. And since it's deterministic, any of them could register it in any context. And if adversary wants to check whether certain APK prime belongs to Alice and Bob, can easily use this canonical check in the system and the individual public keys of Alice and Bob, because key aggregation is deterministic. We know all the inputs, so we can just perform some canonical check. So for the existing multi-signatures, actually, these claimed or wished privacy properties is not achievable. And we define this model, like the model that individual public keys of the signers are public as non-public key models. This is the real world scenario we wish to have the privacy property, and existing ones cannot achieve it. Just to see what is the situation for the existing ones, we define a weaker one. We called it all but one public key model. In this one, we have the same game, but we mainly assume that in each signing group, there will be some freshly generated individual public key, which is unknown to the adversary. So that by relying on the unknown individual public key, we can have the privacy property we define. But obviously, this is not the setting we want to achieve. We want to achieve it in the realistic model. So this means that we can answer the question mark right now, and the privacy property we need doesn't exist for the existing multi-signatures. So we want to get the property one, and for that we need to change the syntax of multi-signatures because we want to support the probabilistic key aggregation there. And for that, supporting this probabilistic key aggregation to get for the application we consider, we will need to change the syntax of it. Just as a recap, multi-signatures with deterministic key aggregation works as follows in general. Again, Alice and Bob can create their individual key pairs and share them and aggregate their keys. We have this deterministic key aggregation. Any of them can register, and all other signers in the group can check whether this APK AB belongs to the signing group or not by using the deterministic behavior of the key aggregation. But this check is crucial because I want to know that I'm a member of this group and this aggregated key, so that I will be convinced that we can authenticate as a group in a secure manner. And then they can create their signature by running an algorithm called mulsign. It outputs some signature shares, and these signature shares can be combined into a final signature, which can be used to authenticate. So we will have a new type of multi-signature, which we call multi-signatures with verifiable key aggregation. Will be clear in a moment. And let's try to build it step by step. So our first aim was having probabilistic key aggregation. So let's just try that we are probabilistic key aggregation additional to the previous scheme. If we have it and we just run the same structure, Alice and Bob will end up in different keys because key aggregation is probabilistic right now. So we don't know which one to use. A simple change would be just making one of them to run the algorithm and share it with the other one. But in this case, we don't know whether this public key indeed belongs to the group of Alice and Bob or not. And this check is crucial for Alice because Bob can just sample some fresh public keys and send this fresh PK as the group public key because it's randomized. And there's no way for Alice to verify if Alice's contribution is necessary for this group. So for that reason, we will need some verifiability for this key aggregation if it will be a probabilistic algorithm, and also non-interactive. And we change the key aggregation algorithm for that. It is probabilistic plus it outputs some proof that can be used by Alice to check whether the proposed group public key indeed belongs to Alice and Bob. And for that, we define a new predicate in the syntax called verify key aggregation. And if this predicate outputs 1, then Alice is sure that Alice's contribution is necessary for the proposed group public key. And then we can just run the syntax as we know. So after this change, we have a ready syntax, but now we also need some constructions. In the paper, we have a BLS-based construction. I will just sketch what are the changes we need to make there as much as my time allows me. So in discrete logarithm-based multi-signatures, we have a very common key aggregation technique we use. Here, you see the existing BLS multi-signature with deterministic key aggregations. I will just point the key aggregation technique there, and I will mention what are some changes we can make, and potentially they could also be applied to other schemes, other discrete logarithm-based multi-signatures. So you don't need to worry about the other algorithms, actually. In the key aggregation, we can just perform some naive multiplication of the individual public keys, but this causes certain attacks in the multi-signature context, and we have this generic technique for the exponentiating with the hash values. So I will not go into details of this, why this technique is necessary. It's kind of generic for the multi-signatures, but the main point here is that we can just tweak this existing nature of exponentiated with hash to have the randomizability property we need. So the main change we will need to make here is simply add some high entropy value there, and just keep it as an input to the hash value. And right now, computing these hash values are hard without knowing the random value. That's the main point there. And in the verified key aggregation algorithm, we can still perform the canonical check when we know the pi, because once we know the pi, it's deterministic again to run it. So we can just do it. And as this proof pi value, an internal value for the group members to just check the verify the correctness of the created key. This will stay as an internal value, so we will have the privacy feature we need as long as this proof pi value is secret, as the syntax also suggests, because proof pi value is not published during the registration. One point here is that this pi value will also be necessary to combine signatures in general, again, for discrete logarithm values. But we can just make our syntax, we can just change our syntax in a way that proof pi will be input for combine, and we will be able to combine the signatures. And the key point here is that we don't rely on the randomness of proof pi for the unforgeability still. It's just there to provide the randomness for the privacy feature, Yeah, that's all. And in the conclusion, we come to a point that we have the long-term keys we want and the group public key privacy we want at the same time. Thanks for listening.
Question?
Sorry, thanks for the presentation. I was just wondering, suppose I'm Bob and I would like to update my key. How does this compare, like, what should I be doing in order to update everything?
Group public keys,
in terms of efficiency, in terms of
public keys, you mean?
yeah.
And you want to create a fresh key pair mainly, right? Just to update your key. I mean, you would have to regenerate all group public keys mainly, but the other members don't have to generate new keys.
And would it do anything to privacy? Like, would it harm the privacy if I update?
No, it would just mean that, I mean, as long as the key aggregation is run in an honest manner, and by honest, I mean that it's indeed run by using true randomness, it'll be fine. So if you just rerun the key aggregation algorithm again and again with by honesty, it will be fine.
So you describe a solution where Bob equals to Alice, that the aggregate is.
Yes.
Right? So it seems that Bob could actually link that is public even without Alice's consent. Can you imagine a setting where they actually get duplicated key by interaction in a way that none of them is able by themselves to actually live there? We have an enhanced privacy.
Yes, it could be done. So the challenge here is that, I mean, mainly we need randomness in the key aggregation as an input, and we need to rely on it. So we could also have an algorithm, we could also have a protocol that both Alice and Bob contributes with some randomness, but once we do it, we start getting an interactive key aggregation algorithm. So it's like, we will have long-term keys, but we will still generate some interactive key generation algorithm. If we are fine with it, it will be doable. Yeah, but our aim was keeping this ad hoc non-interactive key aggregation and see if we have a solution there.
If you allow for interaction, like just some keys.
Like secret keys of Alice and Bob, you mean?
So whatever you generate. It would still be deterministic, but dependent.
So it wouldn't work. So here, as it's just a random value, Alice and Bob can create many different group public keys for themselves, even for the same public keys. It wouldn't work for it. So it's literally like real. It's like key randomizability for the original signatures. In that sense, it wouldn't work. But if we are fine with having a dedicated group public key for Alice and Bob, then it would work. But again, we wouldn't have some unlinkability for Alice and Bob's groups.
I noticed that for the key aggregation, you need some randomness. Yes, and for when you Wi-Fi the signature, you also need the randomness.
Like the same randomness, you mean?
Yeah,
No, for the verification, we will not need it. But to combine signatures, we will need it. Okay. Yeah. Yes, combine is for combining the signature shares of Alice and Bob to a final signature, which will verify for the group public key. So the signature verification is just has the same structure with the regular signature schemes. In that sense, it is oblivious to the process. It could be any public. It could also be public key of any user, individual user actually.
Question? Okay, so let's take
Thank you.
Okay, so so now we are in with the fourth talk on updatable public policy compliance signatures. So and Hendrik will give the presentation.
Yeah, thanks for the introduction. Yeah, so this is joint work with Christian Balica, Manoshi Schmeitra, and Christian Matt. So yeah, let's start with some motivation for this work. And one of the motivations that we consider is the blockchain setting, where we have two parties, Alice and Bob, and both of them are in possession of their key pair. And now we have Alice who wants to create a transaction for Bob. So what Alice does is she takes Bob's public key, like some content of the transaction, and generates a signature over it. Right, and once she publishes this can be verified using both of the public keys, the transaction content, as well as the signature. And now we can think of an extension of this setting where we actually want to be more restrictive and we want to enforce some policy on the parties, right? So this is based on attributes that the parties have. So we can imagine that besides their keys, they have some attribute sets that contains their profession, their age, or things like this. And now we only want to deem a transaction valid if, beside being a valid signature, also both of these parties together fulfill this global policy. And a few years ago, there has been a new notion has been introduced that solves this problem, which is this notion of policy compliant signatures. And here we have a trusted authority in the first step that takes as an input this global policy and outputs a master public key, master secret key pair. Then the master secret key can be used to generate the keys for the different parties based on their attribute sets. And once they're equipped with this, signature generation essentially happens more or less as before. So technically, right, so Alice can use her secret signing key together with Bob's public key to generate a signature. And then the signature can be verified using both of the public keys as well as the overall public key of the system. And yeah, it's only valid if they fulfill the policy. So this also leads us to the security notion that we want to have for this primitive. We first want to have unforgeability, right? Meaning that, for example, no one can sign on behalf of Alice, or they shouldn't be able to sign if they don't fulfill the policy. And we also want the attributes to be hidden, right? So we really only want the signature to reveal this evaluation, but nothing beyond that about the attributes of the parties. So yeah, and one can now ask the question, like, what about updates in the system? Because the setup procedure needs to take as an input this global policy, right? We don't know how to handle this. And this is what we focus on in this work. And we do this by first extending the setup procedure and let it output a token, depending on the policy, besides the master public key and the master secret key. And then we also allow it to run an update procedure to generate fresh tokens for different policies than the initial one. And now we, of course, also have to update the signing procedure, taking as an input this token, as well as the verification procedure, taking as an input this token. And then, yeah, the policy that is evaluated corresponds to the one associated to the token. And yeah, also for this, we need to define unforgeability and attribute hiding. And we do this using a security gate where we have an adversary and we give it first access to a key generation oracle that it can query using arbitrary attribute sets of its choice. And then it gets back the corresponding public key. It has the choice to also corrupt those keys to get the corresponding secret key. It can ask for any update token it wants. And it also gets access to a signing oracle for keys that it, for example, hasn't corrupted, right, with respect to a token as well, and then it gets a signature. And the task for the adversary is to output like some tuple of public keys together with a message and a signature, such that these signatures verify, and that they also satisfy a forgery condition, which is captured using this formula, right? The first one is that the key, for example, has not been queried to the corruption oracle, meaning that the adversary came up with it on its own or tries to impersonate someone, that the policy is not fulfilled, or that the adversary generates something for a token that has not been output by the authority. Right, so now we can also look at the attribute hiding game where the adversary has access to the same oracles, but they're defined a bit differently. First has access to a key generation oracle where it submits 2 attribute sets. The challenger then flips a bit and gives out the key corresponding to the bit. And the task of the adversary is to figure out which bit the challenger has used. The adversary can also corrupt those keys, but now we have to impose some restrictions here to not make it trivial for the adversary to win the game, meaning the adversary can only corrupt have been generated with respect to the same attribute set. It can again ask for updates. And it can also ask for signatures again, but here we need to have like a similar condition, right? It can only ask for signatures for keys that behave the same under the policy evaluation over both of the challenges. Right. So now that we know what we want to achieve, we can look at a way like how to build it. And there's one naive approach that simply relies on the PCS notion directly. So what we would first do is we would run a setup of a policy compliant signature scheme using our first policy at 0. And set up everything, generate keys based on that. And once we want to update to a new policy, what we're going to do is like, we're going to reinstantiate the whole system, right? So we're going to execute setup again for the new policy and redistribute all the keys. But this is, of course, a not so optimal solution, right? Because now the update would depend on the size of the keys that are in the system already, because we need to redistribute them. So we need to come up with something better than that. And we're going to use 3 tools for this. The first one is digital signatures. We also need some non-interactive zero-knowledge proofs, and we need what we call a 2-input partially hiding predicate encryption scheme. So we're now having a more detailed look into what we mean by that. And we start here to first take a look at the single input scheme for public key predicate encryption. So here again, we have an authority that outputs a master public key, master secret key pair. The master public key can then be used by Alice to encrypt something. And the master secret key can be used in a key generation procedure with like a single input policy to generate a functional key. Alice then uses the master public key to encrypt some attributes. And Bob can use the functional key to decrypt the ciphertext and then again only learn a policy evaluation. And here again, we want to protect against any leakage beyond this policy evaluation. So now there's also a 2-input equivalent of this notion. And the main difference here is that besides only generating a single ciphertext, Alice can, for example, generate 2 ciphertexts for 2 different attribute sets, send them over to Bob, and then Bob has a functional key that corresponds to a 2-input function that allows him to run this 2-input function on both of these ciphertexts combined. And here we also want to ensure that besides attribute hiding, it is not possible to change the positions of those ciphertexts. So Bob should only be able to learn F evaluated on the first attribute set and the second one, but not the other way around. And for this setting, it's also actually fine to switch to the secret key setting, meaning that there is only one key that is used for encryption as well as the secret key or the functional key generation. And in this work, it's actually enough to rely on a weaker notion of security, which we introduced as partially hiding. And what we're changing here is that for the first position, we only need an encoding of the attribute set, meaning that Alice still is required to use the master secret key to generate this encoding, but this encoding doesn't necessarily need to hide the attribute set. And this is for the sake that if Bob obtains like a ciphertext for the second position, he's not able to generate anything on his own for the first position, right? So he's always required to get something else from Alice for the evaluation. Yes, so attribute hiding in this case then only holds for the second slot. So now equipped with these tools, like how can we build our primitive? So we first start by defining the master public key, and we include there the CRS of the non-interactive zero-knowledge proof system and 2 verification keys of the digital signature scheme. The master secret key contains the corresponding signing key for those digital signature schemes, as well as the master secret key for the 2-input predicate encryption scheme that we have just seen. And now the idea is to generate a key for the party by generating an individual digital key pair for the user, as well as encrypting their attributes as part of the public key. And then the authority also authenticates this by signing it using one of its signing keys. The secret key consists of something similar, right? So we also have a signed version here of the verification key of the user, but we don't have an encryption of its attribute set, but this encoding that I've mentioned before. And the party, of course, also learns the signing key of this corresponding verification key of its signature scheme. And now the idea on, right, so the token then is simply the functional key for the policy that we currently want to evaluate, again, also authenticated. And now the idea to kind of show that the policy is fulfilled is simply like if the sender, if someone wants to send to someone, they take the ciphertext out of the key of the receiver, combine it with the encoding that they have as part of their secret key, and prove in zero knowledge that this fulfills the policy. And besides this, they of course also have to prove that these are values that have been actually obtained from the authority to prevent forgery. And this is what the signature is for. So to be more precise, to generate a signature, you would generate a zero knowledge proof that the decryption succeeds, meaning the policy is fulfilled, as well as these are the values that you actually have by proving that the signature is valid from the authority. And then, of course, you sign it using the key pair of the user together with the message that you want. Great. So are we done now? Unfortunately, the answer is no, because it turns out that even this notion of partially hiding predicate encryption, we only know how to realize from quite heavy assumptions, meaning like something like I/O. And we would like to have something that is more feasible. So another question could be like, well, can we try harder to come up with a construction that maybe doesn't need this heavy primitive? But it turns out that the answer here is also no, because you can think about in UPCS scheme as a partially hiding scheme, where the public key acts as a ciphertext, the secret key acts as an encoding, and the token acts as a functional key. So how are we going to solve this problem? We're going to solve this problem by introducing interaction, as well as relying on a single input predicate encryption scheme for the policy evaluation and signature generation. So yeah, we're switching to the interactive setting. So the master public key, the master secret key, and the token are quite similar, with the difference that we now also have a master public key for a single input scheme in the master public key of the overall system. We have we also switch the corresponding master secret key to the single input PE scheme, and also the key in the token is only generated with respect to a single input function. Then the key of the party is simply generated as an authenticated verification key. And the corresponding secret key now doesn't contain, again, the encoding of the attributes, but the attributes in plain sight. And now the idea is if someone wants to, if the sender and the receiver want to generate the signature, they're going to act in the 2PC protocol, where they take as an input their respective public and secret keys, as well as the master public key. And then what this 2PC is going to compute, it's going to first verify the information like that the public key that one party inputs actually corresponds to the secret key that the other party inputs. And they're also going to compute predicate encryption of both of the attributes of the parties concatenated together, such that they're a single input. Then the 2PC outputs the ciphertext, as well as a proof that this whole computation has been done correctly to the sender. And then we kind of, to generate a signature, do the same as before, meaning we generate a proof that the decryption outputs 1. Here, the single input policy would first like split the single input into 2 and then internally evaluate the 2 input function. And we would also prove that the ciphertext that we use here has actually been output by this interaction, right? To again have like this input bind to both of the parties. And then, yeah, the user can again sign both of those proofs together with a message and output this as the final signature. There's still a small issue with this solution, though, which is not so nice, is that we require recursion here, because now we have to prove when we generate the signature that the verification of another proof is equal to 1, which is not optimal. But there's a simple fix for this using commitment schemes. So to do this, we are kind of modifying the computation that the 2PC does. And besides only outputting the ciphertext, it also outputs a commitment to the ciphertext together with the opening. And then what happens in the proof generation of the signature is that you don't need to prove anymore that the proof of this computation verifies. but that's just that this commitment commits to the same ciphertext, and then you also include this commitment as part of the signature. This is our final construction that we present. So yeah, to summarize in this work, we define this notion of updatable policy compliant signatures. We present the security notions of unforgeability and attribute hiding. And we presented a non-interactive solution to this problem by introducing this notion of two-input partially hiding predicate encryption, showing that there is an equivalency with the notion of UPCS, and then like resort to the interactive setting to get a more feasible solution in terms of assumption. Yeah, thank you.
Question? There's a work on input attribute-based encryption.
Yes.
Which is what partly like, but I think you really need to be functional encryption here, not like an AB type.
Yes, you always need to do the evaluation on the attributes, right? And the attributes need to be hidden. That's like the main part. If you have something like this, you can use it, right?
Find those ideas with let's say the reusable non-interactive, like a common server beginning, use that. Then so just like the online account.
Yes, you can reduce it. So in the actual paper, we did this all black boxly because we got some issues also when we defined the security with composition, right? Because we didn't want to use a specific instantiation of the protocol. So we wanted to do it all black boxly. So you have to be precise then how you answer a signing query in the security game, right? Because you could imagine if you have an interactive protocol, the adversary could say, oh, I sent the first round, I get back the second round from the challenger, right? And then I do something else before I kind of continue the signing evaluation, right? So this is something, if you want to do something like you said, you have to be careful that this works with the primitive that you're using as an instantiation for the interactive part.
You might be able to still use the 60. And yeah.
Yes. Okay, good.
I have one question. It's about applications. Like,
yes.
So does these interactions like make applications more difficult, or do you have examples where this
So we actually think if you use like even like a 2-round primitive, maybe something non-interactive that's close to non-interactive is even better. But we were thinking as a motivation, it's quite natural, right? Because if I want to send something to you, I think it's okay if I tell you offline first, hey, I want to send you something, and you reply to me, yeah, sure, it's fine. Here's the information that you need, and then you put the output on the blockchain, right? Of course, like if you use protocols, for example, with more rounds, right, then you would need to argue that, okay, we have to speak offline for a while. If you go offline or I go offline, then it might be a bit less optimal. But yeah, since there are 2-round instantiations and we can rely on a trusted setup anyway, I think it's like quite natural to have this single shot kind of interaction.
All right, so if there are more questions, let's thank this speaker again. Okay, so we're ready for the result of the session on proving equivalence class signatures secured from non-interactive assumptions. And Fabian Regen is giving the presentation.
Thank you very much for the introduction. This is joint work with Balthasar Bauer and Georg Fuchsbauer. And yeah, let's start off. I presume you're all familiar with what a digital signature is. So just for the reasons of syntax, we can generate keys, we can sign messages, and then we can verify the signatures. But here we're talking about equivalence class signatures. So what is that concept? And they were originally introduced in 2014 by Hansa and Slamanik, and Fuchsbauer then found a problem in their proof, and together they refined the concept and finalized it in 2019. And they are defined over a bilinear group. So for simplicity, let's just imagine a group, and the messages that we consider are all the tuples of non-zero group elements. And they are partitioned in a manner that two messages are related to each other if they're a multiple of each other. And now, what's a way that we could visualize this so it makes maybe a bit more sense? So consider a message M that has the discrete logarithms alpha and beta, where G is the generator of the group. And we then don't plot them like we would usually plot them, but on the x-axis, we plot the alpha, and on the y-axis, we plot beta divided by alpha, so the ratio of the two d-logs. And then what we get from that is that the classes are exactly all the horizontal lines. So for example, the point 2, 2 here corresponds to the message that's g squared, g squared. So here are the d-logs of the messages. Okay, but if you have a signature scheme and you just partition the message space, you still end up with a signature scheme. So what's the point of doing this even? And the point is that we also have an additional functionality. The adaptation functionality, which takes the public key, a message, a signature, and some factor mu. And what it does is, if the signature is valid on the message, then it returns a new signature where the new message is mu times the old message. And this can be done publicly. So if you have a valid signature, then you don't need to know the secret key of whomever generated that signature to adapt it. And for example, what we can do with that is if we get a valid signature on GG, then we can use this adapt functionality by using, for example, using mu equals 3 to adapt it onto a valid signature on the message that's 3 cubed, 3 cubed. Okay, so why are we doing this? Like, what we want to construct with this basically is that we have an authority, someone else giving us a signature that authorizes us for something. And we then want to use that signature as a permission to show it to people. And we want to do this multiple times while preserving privacy and anonymity. And so, for example, if we're giving a signature on 1-1, then we can re-randomize the signature and re-randomize the message. And as long as one can't tell whether the messages are in the same class or not, then this gives us anonymity. And this is precisely the property we're looking for, and we call it class hiding. That is, if we're giving two messages, ML and prime, then it should be hard to decide if they're in the same class or not. Okay, now I presume you're familiar with the concept of unforgeability of a signature scheme. So we have this unforgery game where the forger is given the public key, then it can ask for signatures on messages, and then it outputs a forgery, and it wins whenever the signature is valid on the message, and it hasn't asked the message previously. But now we introduced this adaptivity functionality. So we completely broke this game because you could just ask for a signature, then adapt it, and you haven't asked the new message before. So what we now, and we of course define the scheme is secure if the advantage is close to 0. For equivalence class signatures, we have to adapt this notion that now it is only, the forger only wins if it forges a signature that's not in the same class as some of the messages it has asked before. Okay, so maybe some motivation on what this could be useful for. And one scenario is we could construct an anonymous authentication scheme for it. And for that, Alice chooses a public key that is just alpha times G. And with every party Alice communicates with every party I, she establishes a pseudonym. And the pseudonym is just this tuple that's mu I times G and mu I times PK. And now if Alice obtains a credential from a party J that is a signature on her pseudonym, then Alice can take this credential and
run the adapt algorithm on it with the factor mu I divided by mu j, and that creates a signature on the pseudonym valid for party I. So yeah, and now you might ask, you could do this also by using zero knowledge proof. So what is the benefit really? And the benefit really is in the efficiency. Like if you would do this zero knowledge proofs, like the proof of the D-log, for example, then you would have to do a zero knowledge proof on every showing. While with this, what we really only need is that we prove that we know the D-log whenever we establish a pseudonym with someone. So only one time per party. Okay, and now why does this preserve anonymity? And the two notions we need is that the message looks random, and that is guaranteed by class hiding, while another property we need is that the signatures that adapt generates should also be random, but that's a bit too technical to go into detail. Yeah, okay. So EQS are really useful for that reason because you gain anonymity without any trust assumptions. And they were used to construct many different concepts, for example, attribute-based credentials, or blind signatures, or group signatures, and many other primitives. Okay, so what constructions of equivalence class signatures are out there? And in the original paper by Fuchsbauer, Hansa, and Slamanik, they had quite an efficient construction. So we're on this bilinear group, and their signatures had 2 elements of the first group and 1 element of the second group, which is quite efficient. So what was the downside of their work? The downside really was that their proof is in the generic group model, and they asked themselves if that can be improved, and on that way they weakened the unforgeability notion, and that's work by Georg Fuchsbauer and Romain Gay, and they proved it from standard assumptions, in particular from SXDH. But sadly, as it turns out, this new unforgeability notion is too weak for many applications. So we have a proof, but the concept is not that useful. Another approach that has been taken by Khalili, Slamanik, and Rakibali, I think, is to construct EQS schemes using CRS. And they also proved it from standard assumptions. But the problem here is really that if we want EQS to have anonymity without trust assumptions, then in the CRS model again, this anonymity relies on a trusted CRS. So either we assume a trusted CRS and get anonymity, or we let the CRS be generated by the reduction or someone else, and then we don't get anonymity anymore. Okay, so naturally we ask the question, is there a scheme that satisfies the original notion, and can that scheme be proven secure from a non-interactive assumption? Okay, so I presume you're also familiar with security reductions. So we look at the forger F as a black box, and we're trying to reduce the problem pi to the unforgery game, and pi would be a non-interactive assumption. And what the reduction does, it gets the instance, it then simulates the game to the forger, and it tries to use that forger to solve the initial problem. And now, really what we can use a reduction for is to make the statement, like the contraposition, if pi is hard and r reduces the problem, then unforgery must be hard also. And to be concrete, we have to somehow measure how good a reduction is. And we call that the tightness of reduction. So reduction is phi tight if given an adversary that wins with probability epsilon, it wins with probability phi times epsilon. And what we showed really is that for any EQS scheme and any problem pi, no reduction can exist. And
how did we show this? We showed this by giving a meta reduction. That is, we assume there exists a reduction that reduces the unforgeability notion to some problem. Then this meta reduction can use that reduction to either also solve a problem, which is a common way meta reductions are used, or solve a different one. And I'm trying to give you a quick overview of what the proof idea is. And for that, sadly, we have to make some radical simplifications. So for the sake of today, let's assume that the reduction partitions the message space into two classes. And one of them is the set of signable messages. So that is all the messages when we run the reduction and we ask for a signing query, then it can answer it with a valid signature. And the second set is the set of exploitable messages, so set E. And that is the set of messages whenever the reduction gets a forgery on that message, then it can win pi. Then it can solve the underlying problem. And yeah, for the sake of this, we assume that the whole message space is partitioned in either S or E. And now immediately we can make two observations, and that is if the reduction were to be a successful reduction, then both sets must be big. Like if the set S were to be small, then if the forger asks for a signature on a message, but the reduction cannot provide the signature, then the forger can just abandon and he has won the game in that instance. While for E, per definition, if there is no messages for which a forgery helps R to win the problem, then R doesn't win the problem very often. And in the same manner, we can also deduce that they cannot intersect, or their intersection must be small, because if there was an element in both, if it was easy to find an element that's both signable and exploitable, then the reduction could solve the problem by itself. It wouldn't need the forger at all. Okay. So how do these sets S and E behave in regards to the classes? And for that, we're going to look at two extreme cases. So remember, the classes were all the horizontal lines. And so in the first case, we consider the case where E and S do not share any classes. So what can we do in this case? And recall the notion of that gave us the anonymity property, the class hiding notion. That is, we're giving M and M prime, and we're trying to decide if they're in the same class or not. And now this setting we can use to solve class hiding by just asking for a signature on M. And for example, it falls in S, and then asking for a signature in M for M prime. And if the reduction cannot sign it, then in this setting, we can deduce that they can't be in the same class. And that observation we can use to construct this meta reduction that gets a problem instance of class hiding, then just samples a problem for the reduction. It asks for the two messages, and it sees if the reduction can sign them or not. And that it does by simulating the forgery to the reduction. Exactly. So this is the very special case where these two sets align with classes. So let's look at a different very special case where there is no correlation between the sets and the classes. And now there is all the classes, half of them are in the set E and half of them are in the set S. And what would happen in that scenario? We can use it to solve the underlying problem efficiently. And how can we do that? We just ask for the signature on the message, then use the adapt functionality to adapt it on a random message in the same class. And with good probability, in that case 1/2, we get a message that's in the set E, and that means that R can solve the problem. Again, we can construct the meta reduction with that, but yeah. I won't go into details here, yeah. Okay, so sadly, in general,
proving this isn't as easy as these special cases because we don't know anything about the sets S and E and how they relate to each other. There can be messages that aren't in any class at all. And we only know that in expectations, these sets, how they behave, how big they are, and how they relate to each other. And so this was quite a technical proof, but the theorem we arrived at is that for any EQS scheme sigma and any computational problem and any reduction that has tightness phi and running time tau, we constructed a meta reduction D, as we've seen before, that attacks the class hiding of sigma and runs in time about 2 tau. A meta reduction M, as we've seen, that attacks pi and runs in time tau. And really a dummy adversary F that attacks unfortunately and runs in constant time. And that adversary SF here represents really an adversary that just abandons. So it represents the case where the S and E intersect and the reduction R can just win by itself. And the statement we arrived at is that the advantage of D winning class hiding plus the advantage of M winning pi plus the advantage of R winning pi by itself must be bigger than or equal to phi to the 5th over 384. And so what does this mean even? What is this statement for? So if we assume that class hiding and the problem pi are hard, then we know that all these advantages of the left-hand side must be small, must be negligible in the asymptotic case. And therefore also phi must be negligible in the asymptotic case. But recall, phi was a measure of how successful the reduction is. And you have a reduction, and if you have a reduction that only wins in negligible many cases, then it's not a very useful reduction. Or the contraposition of that, if we assume we have a useful reduction, then we know that phi is big, therefore phi to the 5th over 384 must be big, and therefore at least one of the advantages must be big, and we can break one of these problems. Okay, so how could we overcome this impossibility, or where do we go from there? One thing to note is this impossibility does not apply to the schemes that were constructed in the CRS model. And the reason for that really is that in our case, the reduction would be able to choose the CRS. And that means that the reduction could choose, it doesn't have to be honestly generated CRS, but it can choose a CRS such that it can then later figure out whether an adapted signature has been seen before or not. And yeah. And those schemes in the CRS model, they were claimed secure under standard assumptions, but a recent paper from Balthasar and Georg showed that their proofs are in fact flawed. So sadly, this does not apply yet. And another avenue that we are taking now, as in where do we move from here, is what happens in the HEM. And we are confident that we can prove that EQS are secure in the HEM also, which is the algebraic group model. But yeah, thanks a lot.
One question about
Yeah.
this slide, so it's under the puzzle. So you're saying that the impossibility result does not apply to schemes in the CRS model, right? So the those schemes are in the CRS model are coming from the standard assumption, but this, I mean, this does not imply that the scheme must be wrong, right? So the fact that you found flow,
No,
it's an independent thing, right?
the fact that we found a flaw in the proof is independent from
Okay.
that, for the exact reason that our proof does not apply for the schemes, because the reduction could choose the CRS and it could choose a malicious CRS where it can then reason about the class hiding.
So it's still plausible that they can be proven from
Yeah,
the assumption.
exactly.
Okay.
Yeah, I have a question on the complexity of the challenger for the unforgeability. Because,
Okay, yeah.
because the challenge of the unforgeability must check that there was no all signature
Mhm.
on a message. But then because of the hiding,
Yeah.
how can you do that?
No, it's not a falsifiable assumption. That's completely true. And that's also one of the problems we're having related to this, that the security definition that we have is not falsifiable, which means that it cannot be efficiently checked. And that is exactly one of the problems they had in their proofs, is that they relied on a lemma from a different paper that assumed that checking the assumption was falsifiable, could be done efficiently, but it couldn't in that case, and that's where their proof broke also.
So I think I have some repercussion on the way that the meta reduction work. Or maybe it's the reduction. The reduction
Yeah.
itself should be able to do something which is.
I mean, the reduction cannot efficiently check it, but that's in the work by Romain Gay and Georg Fuchsbauer that had the weaker unforgeability notion. There they changed the assumption to be falsifiable, as in whenever you ask a message to the signing oracle, you also had to provide the discrete logarithms of the message. And that way you can make the assumption falsifiable. But in general, it is.
Thanks.
Yeah.
I mean, it's not directly related to this, but the problem would be with the weaker unfortunately notion, and the other one is knowing this discrete logarithm. And
Yeah.
that's where GTM and HTM have to, right?
Yeah, I mean, in some sense, yeah. In some sense, you're asking for the oracle lives in the HEM is what asking for.
So anything with some knowledge of exponent assumption be helpful.
I don't know about that. Not sure it's
Any more
Okay.
question? Right, so let's take the speaker and.